Hello everyone. So today we are going to present our ISC of analysis of fluid flow through venturimeter. So we are group of four students, Neha, Sanika, Jayant and Nikhil. So we'll move forward. Okay, so first is the introduction. Venturimeter is the important instrument used to measure the discharge or flow rate of fluids flowing through pipeline. It works on the principle of Bernoulli's theorem, so which state that when the velocity of fluid increases, its pressure decreases. Due to this principle, as the fluid passes through the narrow throat section of the venturimeter, the velocity rises and pressure drops. So it's work on this principle. So a venturimeter mainly consists of three main parts: converging section, a throat section, and diverging section. So the converging section increases fluid velocity. The throat provides minimum area and maximum velocity, while the diverging section helps in pressure recovery because of its high accuracy, simple construction, and low pressure loss. The venturimeter is widely used in water supply systems, chemical industries, oil pipelines, and power plants. Okay, so next we'll see the objectives. So these are some objectives we have referred to perform this experiment or this ISC through using the ANSYS software. So first is the to experimental determine the flow rate of fluid through a venturimeter. To calculate the coefficient of discharge of venturimeter, to understand the working principle based on Bernoulli's theorem, to perform the CFD simulation of fluid flow through venturimeter. This is our main objective of this ISC. To study the pressure variation from inlet to throat and outlet sections, to analyze the velocity distribution inside the venturimeter. So we have analyzed the velocity distribution through using the velocity contours. In the result section, we'll discuss about that. To compare the experimental setup results with CFD simulation results, as we have talked about this. So to validate the accuracy and reliability of the CFD model, to understand the industrial applications of measuring devices, to enhance the knowledge of fluid mechanics and simulation techniques.
Now I will discuss the key principle of interrogator. Specifically it works on the Bernoulli's theorem, and it consists the different sections like converging section, throat section, and diverging section. When fluid enters the converging section, the cross-sectional area gradually decreases because of fluid velocity increases, and as the fluid reaches to the throat section, the area is started minimizing, and the velocity becomes maximum, and the pressure becomes minimum. After that, the pressure difference between the inlet and outlet throat section is measured using manometer. The pressure difference is used to calculate the discharge of fluid or flow rate of the fluid passing through the pipeline. And after that, the diverging section where the area gradually increases, and the resulting in a decrease in velocity and partially recovering the pressure. We display the setup of the venturimeter. Here is the throat section, and we attach the manometer. Here the entry of the throat section and outlet of the throat section. Here the this is area is gradually increases. That means this is diverging section, and here the area is gradually decreases. That is the converging section. Here is the manometer which measure our flow rate, and here is the measuring method.
In this slide, there is observation table. Starting with our experimental data, this observation table summarizes the readings taken from our test rig. We recorded the manometer differences at and the time required to collect a specific volume of water. These baseline measurements allowed us to calculate the actual discharge and mass flow rate across three distinct trials. So on this slide, there are calculations. Using those physical readings, we moved on to our core calculations by applying the standard flow rate formula and comparing our actual measured discharge against the theoretical discharge. We determined the venturimeter discharge or the coefficient of discharge. So the next slide is about CFD simulation setup. To validate these physical findings, we performed a numerical analysis using ANSYS Workbench. We modeled the exact geometry of the experimental setup featuring a 25 mm inlet that converges to a 13 mm throat. To ensure accurate computational results, we generated a tetrahedral mesh containing over 22,700 nodes. The next slide is about boundary conditions. The simulation, a real life thing, we established three primary boundary conditions. We defined a specific velocity inlet, an atmospheric pressure outlet, and applied a non-slip condition along the pipe walls to account for the fluid friction. The setup was critical for accurately analyzing how the pressure and velocities vary. So these are the images of the simulation. So as you can see, first images of the geometry. Second one shows the aspect ratio of the geometry. Third shows the skewness of the geometry, and fourth one shows the pressure counter of the geometry.
So in this slide shows the velocity result. The red color indicates high velocity while blue shows low velocity. We can observe that velocity increases significantly at the throat section because the cross-sectional area decreases. This follows the continuity principle where fluid speed up in narrow passage. And next is a pressure result. Pressure result shows the pressure is higher at inlet and outlet wider section while it drops at the throat. This is based on Bernoulli's principle where higher velocity causes lower pressure. And next is the temperature contour. Some plots also indicate smooth flow developed through duct. The streamlines pattern confirms proper flow acceleration and deceleration in the converging and diverging section. The next slide is CFD result. CFD result. This slide shows CFD result. We can see the previous various contours, velocity, pressure, and temperature. Now, from the table reading, one shows total pressure as 1310.16 Pascal, and second reading shows 1051.99 Pascal. This clearly indicates that pressure decrease at the throat section of the venturimeter. These simulation values help us compare practical readings with theoretical results. Next slide is result and analysis. This slide we analyze the flow behavior and pressure behavior